All right. Last part of this chapter is magnetic materials. So this part, it's funny because magnetism is easiest to explain in terms of electromagnets, but the magnets everyone's familiar with are permanent magnets, right? And those are actually way weirder than electromagnets because there's no current, right?
They're magic.
Or is there current? It turns out there's kind of current, and it's the current of the individual electron all by itself, because an individual electron has spin, okay? Which means you have a charged object that moves. It's quantum spin, so it's a little bit less like spinning, but you can kind of, in a rough way, approximate it as a spinning charged particle, okay? Which means if you have a spinning charged particle, you have current, and that means you have a dipole, okay? Which means the smallest piece, the smallest magnetic dipole you can get is an electron. It's also the smallest charge you can get, right? So this creates a tiny, tiny, tiny magnetic dipole with its own magnetic moment, all right? And it turns out all materials are made up of a bunch of tiny dipoles, just like all materials are made up of positive and negative charges. But remember, for the most part, materials are neutral. It's not because they don't have charge. Why? Why are they neutral?
Because they equal out.
Yeah, they have an equal number of positive and negative charges. They're pretty much spread out evenly. And so as a bulk effect, you don't have a net charge on the object, okay? Non-magnetic materials, pretty much the same thing. Every atom, every electron has a little dipole, but since they're all oriented randomly, your overall effect is that you don't have any bulk magnetic properties, okay? So when you add up all these random magnetic dipoles, they all cancel each other out, and your net magnetic field is 0, okay? That's for non-magnetic material, which is most things, okay? This is a non-magnetic material. Actually, there's not a lot of good examples. Most of this is a non-magnetic material, the desk, okay? Permanent magnets, all you have to do is line up these spins, okay? This is sort of a rough approximation, but basically you have a bunch of tiny magnets. If they're all lined up, it acts as a big magnet, okay? So this would be the North Pole, this would be the South Pole, and the bulk effect is that you have a magnetic field. Now this explains why when you cut a magnet in half, right, if you cut this in half, you can see this side's still north, this would be south, this would be north, this would be south, because you can see the pattern is still the same inside the material at the microscopic level, okay? As long as you just have a bunch of dipoles lined up, whatever is near the pointy end of the dipole, right, the north side of the dipole is going to be north, whatever is at the south side of where these dipoles are pointing is going to be south. And you can cut it down all the way to a single layer of atoms and still get north and south, okay? So, there are no magnetic monopoles because the very most fundamental kind of dipole is an electron. And since you can't cut the electron in half, and since the fact that the electron is spinning is what creates this dipole, that means you cannot break it down into like north and south. It's always north and south stuck together, okay? So no matter how you cut up a magnet, there will always be a north pole and a south pole. If you try to cut up an electron, well, that's just going to be really hard to do in the first place, but you can't really cut up an electron, and even if you did, it would inherently get rid of its magnetic properties, and then you still wouldn't have a magnetic monopole. You would still have either dipoles or nothing, okay? So, more realistically, I mean, we know a permanent magnet looks like this. We sort of treat it as this is the dipole. Okay, it's made up of all this microscopic stuff, but the net result is something more like we have a giant dipole. Okay, but more realistically, we have these ferromagnetic materials. Okay, and for ferromagnetic materials, these are materials that have inherent magnetic properties. Can you think of why it's called ferromagnetic? Iron, yeah. Iron is the most common ferromagnetic material. What's the atomic symbol, the periodic table symbol for iron? Fe, okay? So, yeah, yes. came prepared. Does that say I wear this? Okay. Yeah. All right. So, iron is the most common ferromagnetic material, but there are other ferromagnetic materials. What happens in a ferromagnetic material is these dipoles tend to line up, but they don't usually line up perfectly. Okay, and not all iron is a perfect bar magnet. They usually line up in what we call domains. So a bunch of them line up this way, and then a bunch of them line up this way, a bunch of them line up this way, and they're all next to each other. So you get like little chunks of nice alignment inside your material. The way we actually make a good permanent magnet or semi-permanent magnet is you put this magnetic material, which has all these domains. I mean, how do you think you can get these things to line up? What?
Run the current through it.
Yeah, or you can make a bigger magnetic field, right? All of these little dipoles will line up with the magnetic field, and then they'll pretty much stay there because there's no. You put in energy, you get them into a particular state, and then unless you add more energy, they pretty much just hang out like that. Okay? So if you put them in a giant magnetic field, they have a tendency to all line up in the same direction, and that's what we use for permanent magnets, right? We usually have to remagnetize them periodically because as time goes by and things happen, this goes back to being more random, okay? So an external magnetic field creates an induced magnetic dipole in a ferromagnetic material, okay? How do you think you can mess up a magnet once you've done this to it? Yeah?
Heat it up.
You can heat it up. You can hit it with a hammer, right? You can put energy into the system that will randomize this once again. So, because remember, second law of thermodynamics says if we add energy to something, right, the natural state is just equilibrium. So randomness is the natural state of things. So if we add energy back into the system and we don't do it strategically, like putting it in a giant magnetic field, it'll just randomize, okay? And this is why it's actually fairly effective to hit old hard drives with a hammer, right? Because all the information is stored magnetically, and if you hit it with a hammer, that randomizes the little magnetic dipoles, and you no longer have usable information, okay?
Not like people slap their computers.
No, that's just primitive monkey brain stuff happening. I always think of that scene in Zoolander when they're like, the information is inside the computer. So anyway, so you can line up all of the domains of a ferromagnetic material by putting it in a big magnetic field. Now usually this doesn't mean putting it next to some big permanent magnets. It usually means sticking it in an electromagnet. And actually we do that with the magnets we use for the lab, right? After people use them for a few years, the magnetic fields get weaker and they do weird things. Like you'll notice if you had a bad one, sometimes it doesn't always go north to south. There's like a weird north like in the middle, okay? And your magnetic field lines get all screwed up. When I start seeing that, when I grade them, then we stick those things in a big electromagnet and we make them proper again. Okay,
I
so we have to like
magnetic north was like making it go towards the middle, and that was our explanation.
It does. Sometimes it does.
Okay.
That usually happens farther from the magnet. But if you're getting weird stuff close to your magnet, that's because your magnet's messed up.
Oh yeah, that was close to magnet.
Yeah. So that happens every few years. We stick them in a big electromagnet. We get all their domains lined back up, and then they behave better again. Okay. The other thing we notice is like over time, the compasses will start pointing in the wrong direction.
Yeah,
couple.
Yeah.
Because those poor little compasses have been next to giant magnets a lot, and they don't know what's going on anymore.
Yeah, that's what we noticed. Like once you put it like while we were doing it, if it touched the magnet, like it was dead. Like that was.
You always have to test your compasses to make sure they are pointing north. Which way is north in this room, by the way? Yeah, it's that way. So if your compass doesn't point north, then it's probably not magnetized properly. This is a lesson I learned. When I was like in second grade, we did like a thing on magnetism in like second grade. And I had this cool compass from REI, and it never worked properly again after that. It was very sad. Anyway, here's a question. All right, the answer is E, which is both A and C, because remember, you're either going to attract one side to the north and one side to the south, or vice versa, because this thing also has a dipole. Okay? All right. That's the end of this chapter. One thing we did skip, which is not super important, but you should be aware of, is ferromagnetic materials are materials that naturally line up with the magnetic field. Okay? There's two other kinds of magnetic materials called paramagnetic, which is just anything that sort of interacts with the magnetic field, like, for instance, a paper clip, right, but doesn't become magnetized easily. Okay, so it has some inherent magnetic properties, but it's not a ferromagnetic material. And then diamagnetic materials actually oppose magnetic fields. So if you put a magnetic field, they'll actually reduce the magnetic field in that material. So what does that sound like? Yeah, like dielectrics, right? So a diamagnetic material can increase the amount of magnetic energy you can store in something like a solenoid, much like a dielectric can increase the amount of electrical energy you can store in a capacitor. Okay, so those get used in solenoids a fair amount.